In this video, we will solve combined loading problems. In problem 1, we have a saw which is stretched with 40 newtons and 2 sections, and in each section, 1 point is given, and the stresses in these points A and B are asked. Well, here are the dimensions. First thing we have to do is to cut. Let's start with section where point A is present, and when you cut, you can take this part, and here you know that the force stretching the saw is 40 newtons, and actually these two are not known. So you have a normal force and the bending moments. So when you do write the equilibrium equations, so you can easily find out that this n value should be equal to 40, and this moment is 40 Newton times 0.1, and the loadings in section where point A is present are a normal force and a bending moment. We know these both create normal stresses. Due to the normal force, we have force divided by the area. So minus 40 divided by the area. And in section AA, well, if you imagine that this section looks like this, and you apply a bending like this, so in point A, you will have positive tensile stresses, which you can calculate with this formula. This is your bending moment. This is the distance of point A from the neutral axis. It is 0.004, and this value is the moment of inertia around this bending axis. So superposing, that means the effect of normal stress and the bending moment will give you a total of 123 megapascal tensile stress. Next, we have to investigate the point B. We cut there, and this is your external load, and in the section, in order to have equilibrium, it's very simple. The shear force 40 Newton and bending 2 Newton meter must be acting. So I have to calculate first the sigma. What do I have? I have a bending moment and the shear force. This shear force will create a shear stress, and the bending moment a normal stress. For the normal stress, when you bend like this and you consider the point B, you will have a tensile stress, bending moment, the distance to neutral axis, and moment of inertia. Your sigma in B is 62.5. Now, what about the torque? So as you see here, you have a section and your force is 40 newtons. So we know that if you have a shear stress, the stress distribution will look like this. In the middle, you have your tau max, and on the surfaces, they are 0. And my point B is over here on the surface. So the tau B must be 0. So your shear force will not create any shear stress. Next problem. Find the stress in point C, this section. Okay. So here we have two supports. One support in A. This would have AX and AY support forces. And here you have a force B, which is perpendicular to the point where the roller touches the beam. Okay, what do we have? We have 1, 2, 3 unknowns. Using the equilibriums, for example, you can take sigma MA and calculate this value, and you can write down sigma Fx and sigma Fy equal to 0, and you can find these support forces. In summary, well, we do not go into details, but we can assume that we can find the support forces very easily. Next step is to find the stress in point C. For this, we have cut over here, and this time we cut the left side. Okay, and the left side. So in this section, well, the possible forces are the normal, the shear forces, and a bending moment. So using this time this free body diagram, you can calculate the normal shear and the bending. Do this, you find that the normal force is 16, shear is 21, and the moment is 32 kilonewton meter. Now we have the internal loadings in our section. Next step, I have to calculate the effect of each internal load on the section and draw the stress distribution. First, I have a normal force, which is compression. This I divide by the area and find the uniform compression stress. Next, the shear force. Acting this way, the stress distribution will look like this, maximum in the middle, but I am interested in point C. My point C is on the surface where the tau is 0, so nothing to calculate. The shear stress due to the shear force in point C is 0. Bending. I have a bending like this, and the stress distribution will look like the neutral axis is in the middle, the stress on the neutral axis is 0. At top we have negative, at bottom we have positive. When you put for the top part plus 0.125, and this is my moment, and this is my moment of inertia around the neutral axis, you find that the stress in C is minus 63. I have everything: normal, shear, bending, and for point C, I can make a superposition, or for any other point, you can do the same. In point C, sigmas are minus 1.3, minus 63, altogether minus 64.5. And the tau in point C is 0. And this is the volume element showing the combined stress state in point C. Well, in this video, we solved two combined loading problems and made stress analysis for certain points. Thank you for listening.